Hello, this is Jacob Dawes from Oregon State University. Thanks for dropping by our virtual poster on modeling and design considerations for resistive impedance-based flow cytometers.
So just to make sure that we're on the same page, flow cytometry, if you're not familiar, is where you are counting and often characterizing populations of cells. This is conventionally done with an optical approach, but recent developments in impedance-based flow cytometry have shown it as being a promising alternative or something to use in addition to the optical approaches. This is especially the case for point-of-care applications where it's important to reduce the amount of infrastructure and high-cost components. So typically, if you're designing a system like this, you may use something like finite element analysis to model the electrical or fluid components, or you may use just an equivalent circuit model. But what we were interested in doing is coming up with a computationally simple method of modeling and simulating these systems, while including things like channel geometry, electrode geometry, as well as purely electrical requirements such as bandwidth. To give a brief overview of how we split up the blocks in this model, you have the transducing block, which is converting the physical phenomenon of the particle transiting over the electrodes into an electrical resistance. And then you have an equivalent circuit model block that converts that into a current given some stimulation voltage. And then finally, that current is amplified with the transimpedance amplifier into a voltage that can be read with some instrument. The trickiest part of this is, of course, trying to transduce the physical movement of the particle into a resistance. So just to really quickly give a brief explanation of how this works. You take your electrode pair, you slice it up into n slices. Your resistance is going to end up being the parallel combination of all the slices that are unaffected with the one slice that has a particle disrupting the electric field lines. So to compute this, you can think of some function representing the particle physically, and you can convolve it with some other function that you choose, which represents the density of field lines across that slice of electrodes. From there, you can make a parallel combination of that slice with the rest of the slices to find the time-dependent resistance. From there, you can use that to calculate parameters for your equivalent circuit model. So as expected, below some corner frequency, you won't be able to take very good resistive measurements because the double layer capacitance will be dominating. But above that stimulation frequency, the peak frequency of the particle's signal should be proportional to the speed of the particle and inversely proportional to the width of the entire electrode set. To test this idea, we built a test wafer with SU8 microfluidic channels on glass. As expected, the peak frequency does correlate well with particle speed, and for some sizes, it seems to follow pretty well with the trend that we predicted. Additionally, when we try to simulate multiple particles transiting the electrode simultaneously, it matches pretty well with observed phenomenon. Thanks for listening, and let me know if you have any questions.